Welcome everyone to my channel. This is my first lecture about the transcritical bifurcation. I am Dr. Bakil Mandal, Assistant Professor, Department of Mathematics, SR University. So first we are need to know what is bifurcation. So bifurcation is a point where the system changes long-term behavior because you tweak a parameter just a little bit, and one moment the system behavior one way and suddenly boom it switches. For example, imagine a population of animal that grows or decline depending on resource. As you increase, the growth rate change may seem fine at first, but eventually at some critical value, the system split into two possible outcomes. That splitting moment is a bifurcation. You did not change the system rules, you just changed the parameter, yet the entire future behavior shifted. So for this lecture, we discuss first various type of bifurcation, then we discuss our bifurcation, transcritical bifurcation. So in our continuous model, we have mainly two types of bifurcation. First one is one parameter bifurcation, second one is two parameter bifurcation. For one parameter bifurcation, we have transcritical, saddle node, half, backward bifurcation, peaceful bifurcation. For two parameter, it is Bogdanov-Taken bifurcation, and it is also known as BT bifurcation. It is also known as BT bifurcation. And another one is Kauf's bifurcation, and third one is Bautin or generalized Hopf bifurcation. So first we discuss the transcritical bifurcation in graphical. So for transcritical bifurcation, if we consider two dimensional model with dx dt dy dt, then for transcritical we need minimum two type of equilibrium point. For example, we consider a model dx dt is equal to fxy, and consider dy dt is equal to gxy. We just consider, and also we assume that the system have three types of equilibrium point. First one is E0, which is 0, 0. Second one is E1, which is maybe X0 type. And third one is E star, which is known as X star, Y star. Now we know how to transcritical bifurcation works graphically. Then we're going to analytically. So here look. So first we consider at a parameter, we consider a parameter value a equals to a is the parameter value where critical value is a star. So first we assume that when system is a less than a star, the equilibrium point E0 is stable. E0 is stable. So if we plot this one, so if we plot, just check. Sorry. So this is our a star. This is the a parameter. So before a star, in this region, E0 is stable. After the increasing of a star, E0 become unstable. E0 become unstable. When E0 become unstable, one scenario we observe that when E0 is unstable, we have a equilibrium point E star. We have an equilibrium point E star. Here E star is exist and it is stable. E star is exist and it is E star is stable. So here we observe that one equilibrium point E0 is change the stability and one equilibrium point exists. This is the main concept of transcritical bifurcation. So there are two conditions needed. One is one equilibrium point change stability and another one same time another one exist or destroy. So for this we consider a specific model. So we learn more better. So we consider specific model. We write dx dt is equal to rx 1 plus ky minus r0x minus r1 x square minus mx square y by a plus x square. And we have ui dt is equal to beta mx square y by a plus x square minus dy minus qey. Before going to prove the transcritical, we just little bit explain this model. So in absence of predator, R is represent the prey's growth rate. This is the growth rate of prey. Is a growth rate, and this parameter k is known as pair parameter. This is death rate. This is also death rate due to interspecies competition. This is also death rate. This is known as functional response, whole known as functional response. Functional response where M is known as consumption rate. M is known as consumption rate, while A is said to be half saturation constant. Now going for second equation, beta is known as conversion efficiency and beta value always 0 to 1. And G is the death rate of predator. This G is known as normal death rate. And this is known as harvesting. So this is Q is catchability effect and E is the harvesting effort. E is the harvesting effort. So this is our model. So first we find is equilibrium points. If we find the equilibrium point, we already check this system have three types of equilibrium points. First one is E0. What is E0 means? Is 0, 0. It is also known as trivial. Second one have axial, predator free axial, and this is R minus R0 by R1 0. This is called predictor free axial equilibrium point. And another we have the system have E star, it is external, it is interior. If we solve these two equations, dx dt and dy dt equal to 0, we have these three types of equilibrium. Because of complexity of model, we could not find the explicit value of x star y star. So far we assume this x star y star is the solution of this system of linear equation. Okay. Now we want to find the stability. So if we find the Jacobian matrix of each point, so first we find the Jacobian eigenvalue, not Jacobian. Fine. We can find first eigenvalue. So eigenvalue of E0 after finding Jacobian, then putting the 0, 0, we have the eigenvalue of E0 is E0, 0, 0 is R minus R0, and second one is minus EQ minus D. Minus EQ minus D. So minus EQ minus D. So here look, this equilibrium, this eigenvalue is always negative, and this eigenvalue negative and positive depend on this condition. If we consider R minus R0 less than 0, that is R minus R0, so this equilibrium point E0 is stable. If we consider is R minus R0 greater than, we assume R greater than R0, E0 is unstable. So here look, the condition of the stability and the existence of U1. Here look, existence of U1 means this equilibrium exists if and only if when R greater than R0. So now check, if R greater than R0, therefore E0 is unstable. Check, if we check the stability, if R equals to R0, then E0 is unstable. So it can be observed that if E0 is stable, if E0 is stable in the situation U1 does not exist. U1 does not exist. If U1 exists, if A1 exists, then E0 must unstable. So if you check, one equilibrium point is change their stability at R equal to R0, and one equilibrium point exists at the same point. So this is the point where the system experiences transcritical bifurcation with respect to R. If we plot in graphical way, so what we observe, if we plot, so this is our parameter R, we consider this is R0. So first we plot E0, 0, 0 is stable when is R less than R0. So it is stable. So in this situation, E0 is stable. In this situation, E0 is stable. So here we written E0 is stable. When increase are when it is R greater than R0, E0 is unstable. So in this situation, E0 is unstable. E0 is unstable. When E0 become unstable, you also observe that one equilibrium point is exist. So we plot this one. So in this situation, one equilibrium point exists, and we know that this is a interior. This is axial. Sorry, this is axial. So in this situation, is E1 exists and it is stable. So now again we repeat. So one equilibrium point change the stability, stable to unstable at this critical value, and at the same time one equilibrium point exists, E1 is exist. I hope everyone understand this transcritical. Now if we plot the phase portrait in these two regions, that means if we plot the full phase portrait of greater than R less than R0, in this situation E0 is stable. That means if we consider initial value here, all R goes to the scene of this. If we consider initial value here goes to here goes to here, like that. If we consider initial value here goes here. If we consider value here goes to here. So in this situation, both population are goes to extinction because of E00 is exist. Now you plot a phase portrait when is R greater than R0. So in this situation, system have two equilibrium point. This is one and this is another one. So if we choose the initial value here, it is come to here, come to here, it is come to here, to choose initial value here, it is come like that. So all the solution trajectory are goes to the basin of E0. So it's an E1. So in this situation, only x0 is stable. X means here is r minus r0 by r1 equal to 0. So in this situation, only x population can survive. So here look, this biological implementation of this with the increase of growth rate, when growth rate of prey is less, then both population goes to extinction. With the increase of growth rate is at the critical value R0, then we observe that prey population can survive. So this is the biological implication of transcritical bifurcation. Now we check how to prove this transcritical bifurcation theoretically using Sotomayor theorem. Using Sotomayor theorem. So before using Sotomayor theorem, we note we need three. For Sotomayor proof of Sotomayor theorem, we need three conditions. First condition of Sotomayor theorem is sorry for this. So here we discuss the proving the transcritical bifurcation by Sotomayor theorem. So Sotomayor theorem. For proving the transcritical of Sotomayor theorem have three properties for transcritical. First property is WT F R is 0 R equal to RTC. First we written, then we explain step by step. Equal to 0. Second condition is WTTFR is 0 R equal to RTC. V equal not is equal to 0. And third one is WT T square F is 0 R equal to RTC V1 V2 not equal to 0. This is the three conditions we want to check step by step. So first we check first condition. See, here first condition say, first we check the first condition. So here, so first we define F. So F means our system. F means our system. So we assume this is our system F, this is our Z. We just assume. So F is F and Z transpose. Now our first step is we want to check transcritical at which value R equal to R0. So consider R equal to RTC is a critical, and in our system is R0 is our critical value. So first we find FR, that means partial derivative with respect to R. So if we find the FR, so R means the growth rate, and growth rate exists in the first equation. So first equation maybe is become 1 plus ky, remaining not same, it is 0. So FR is given this x by 1 plus k1. So now we put in the value is 0. So FR putting is 0 along with R equals to R0 because RTC is the same. So yeah, check. So if you putting E0 at this equilibrium point, so x equal to 0, y equals to 0, it is given 1, 0. Now discuss what is WT and what is V. So if we find a Jacobian matrix at this critical value, we have okay, if we find the Jacobian matrix, we have 0, 0, 0 minus D minus E2. So the matrix have 0 eigenvalue. Now we find the eigenvector corresponding to this eigenvalue. So we have V equals to 1, 0, T, and find the eigenvector of the matrix A transpose is also given. We consider W equals to 1, 0, T. So here WT means 1, 0. So previously find FR previously find AFR. Now we find, so you just multiply by WT. So if we multiply WT, so here we can get, here only one thing. So here we can get 0, 0. So if we use this, putting this value of this equation, we have or 0, 0. Now we checking our second condition. Second condition is, so we now check second condition. So second condition first, check first we find the this value GFR. So previously you already find FR. This is the value of FR. This is the value of FR. If we G means the derivative. So if we derivative with respect to X, we have here the second things. Here we find the DFR. It is given 1 by 1 by 1 by ky. If we find with respect to y, it is given minus x by k 1 plus ky, then whole square, and these two are 0, 0. Okay. Now you putting the critical value is 0. If you put the critical value of E0 at DFR, we check, we have 1, 0, 0, 1. The second condition we use multiply V. V means, here you find V means here 1, 0. So if we multiply by 1, 0, we have 1, 0. And again multiply by WT here. Again multiply by WT. So WT is 1, 0. WT is 1, 0. If we multiply, we have 1, which is not equal to 0. So our second condition is satisfied. Now we check third condition. For third condition, here we given, here expression is G square F. So first we know what is G square F. G square F is del square, first we can F del x whole square into v1 square plus 2 into del f del x del y v1 v2 square, so square plus del square f del y then whole square, it is v2 whole square. Similarly for del square g del x square v1 square plus 2 into del square g del x del y v1 v2 plus del square g del y square v2 square. So this is the del square full matrix. So what is b1? B1 means here b1 means 1 and b2 means 0 because eigenvector is 1 0. So if we partial derivative f means the first equation dx dt with respect to x, we check, we have minus 2r1 because f to 0, so we no need to check this remaining term, no need to check this term because b2 is 0, whatever the calculation is given is become a 0, we not check. And also for second equation we not check because you not formula here we check is multiply by wt, finally multiply by wt. Wt means is 1 0, so whatever the second equation is given is multiplied by 0, so it is become a 0, so it is become a 0, so no need to calculate second one. So now we're going to condition again. So if we write the condition is wt g square f is 0 r equal to rtc v1 vv. So it is finally given wt means 1 0 and this whole things given is minus 2r1, something is number a, maybe we consider maybe is a number, big number is a. So if you multiply we have minus 2r1 which is not is equal to 0 because r1 is parameter and r1 is greater than 0. So by Sotomayor theorem we can say that the equilibrium point E0 is experience a transcritical bifurcation with respect to parameter r at r equal to rtc, or it is known as r0. So this is the theorem. I hope everyone understand. Thank you so much for listening.